So here's an important concept. Every operation or function that we have has exactly one inverse or opposite operation. So if we think about this, we know a lot of them. What is the inverse of addition? Subtraction. And if we were using this to solve, we would subtract the 3 to the other side to solve for x. That's how we were solving equations using inverse operations. What if we had multiplication? What's the inverse of multiplication? Division. So if we were trying to solve, wow, I just almost wrote the word divide. Division. If we were trying to solve for x in that little example, we would divide both sides by 3. You guys discovered this last class with our question stack. What's the inverse of cubing? Cube root. Yeah, it's the square root symbol with an index of 3, which is called a cube root. And so we'd cube root both sides to solve for x. So here's a follow-up question. What if we had an equation like we did at the beginning of this unit that was 3 to the x equals 7? That's an exponential. What's the inverse of exponentiation? Like, how do you get that x out of the exponent?
Square.
Yeah, but that's when there's a number in the exponent. How do you get rid of an x in the exponent?
You square root the x.
These are all great ideas, but in fact, I have to introduce to you an entire new type of function called a logarithm. Logarithms are the function type that are the inverse operation of exponentiation. Interesting, right? Recently, we learned about these exponential functions and their properties, but since these are inverse operations, and we just studied inverse functions last class, before we really get into logarithms, we need to talk about how we go back and forth between these two processes. The same way you would like do add and subtract, multiply and divide, square and square root, we need to know about exponentials and logarithms. Just as we can write rational numbers in decimal and fractional form, we can also write equations in exponential or logarithm form. And that's one of our main ideas for today, is being able to go back and forth from exponential to logarithm or logarithmic form. These forms create equivalent statements. So I'm not changing anything. I'm just like writing it as if I was going from decimal to fraction, just a different representation. We are rewriting it. The way that we are rewriting it is called the log loop. Now, in your previous classes, you may have done the log loop differently. Here's how I teach it, and here's how I want you to think about it. These are equivalent expressions. We have the base b raised to some number a, and it's equal to c. So example, what if I had base 2 raised to the second power? That would be equal to 4, correct? We can rewrite that in its inverse form, in its logarithmic form, by keeping the bases the same. So notice the base is here as a base. The base becomes a subscript behind the word log. It's a subscript of the logarithm, meaning it's the base of the logarithm. And then notice that all that happened is like the a and the c switching places. Yes? That's called the log loop. They are looping around. And this makes sense because last class we learned that all you do is switch the inputs and outputs when you're doing inverse functions. So all we do is switch the a and the c value here, the x and the y, if you will, the input and the output, to make this happen. So here are our notes to ourselves. The base will never change. It just needs to make sure it tracks and goes to the same spot. So our base never changes, but what we will do is we will loop or we will switch the input and the output, which makes sense because, again, that's what we learned last class in section 2.8 about inverse functions. They just switch the inputs and the outputs. I'm hoping this is a review, but like I said, I'm pretty sure when you learned this last year in Algebra 2 or whenever you took Algebra 2, it was either skimmed or it was at the end of the year. So, like, it was the end of the year. You had all the end of year things. Who knew how long you were in class for? There are two special cases of logarithms that have a special notation. A common logarithm is a logarithm, A logarithm with a base 10. So if we say log base 10 of 3, we can just write that as regular log 3. We see that? Look at your calculators right now. Do you see the log button on your calculator? It just says log. So we can actually find the common logarithm very easily on our calculator because we're just going to press log and then 3, close parentheses, enter. There is a second special case logarithm called the natural logarithm. The natural logarithm has a base of the natural number e. So instead of writing log base e of 3, we will call it the natural logarithm. Do you see the ln button on your calculator?
Yes.
Right underneath log, right? Yes? That's the natural logarithm button. So we very easily can evaluate natural logarithms on our calculator. So keep that in mind. A log with no base showing is base 10, and ln is base e. First thing we're going to do is practice being able to convert the equations from exponential to logarithmic form. Remember, the base never changes. So if we're doing this problem right here, 3 to the second power equal to 9, which is true, correct? 3 squared is 9. We want to switch this into logarithmic form. What is the base? 3. So we're going to go log base 3. Notice that it is a subscript, which means it should be smaller and underneath, kind of like a comma of the G, a subscript. Then I'm going to switch the inputs and the outputs, which means what should be the next number that I write? 9. And what should it be equal to? 2. I have switched the inputs and the outputs. The output was 9. That becomes the input. The input was 2, that becomes the output. Log base 3 of 9 is 2. That is a mathematical fact that we are going to have to know. Log base 3 of 9 is 2. The same way we know 3 squared is 9. Let's try this one. What's the base here? 10. So I can write log base 10 of, and then I need to switch the inputs and outputs. Yes, y equal to x. Now there's a sneakier way I can write this. What did I just tell you is the way we can write base 10 logarithms? Not putting anything, correct. So really, and the way you'll probably see this is log of y equal to x. We know that that's log base 10. So if they don't show you a base, it's base 10.
It's not 1 no more.
It's not 1, it's 10. 10 is the invisible number for logarithms. What's the base here? R. So how would I write this in logarithmic form?
Log R W.
So we would say log base R
Log base R
of
W equals T.
equals T. So again, we're switching the inputs and outputs, keeping the base the same. Now what about this last one? What is the base?
Wait.
E is the base. The base is the thing with the power. So what has a power here? E. So we're gonna put down log base E. Now here's where it's interesting. We do need to switch the inputs and the outputs. What was the output a second ago?
For which one?
For this one, what was the output? Y. That becomes the input. What was the input? That becomes the output. Now there's a sneaky way we can write this one too. What did we just say log base E can be written as?
10. Oh, I would.
That's a common logarithm, base 10. What about base E? Look right above this. Look right above this.
Basic log.
Oh,
ln, the natural logarithm. So we're going to rewrite this as natural logarithm of y equal to 3x. If you're wondering why I just wrote that in cursive, it's because I taught this class 2 or 3 years ago, and for half of the entire semester, everybody thought I was writing IN. That's an L. So I'm going to write it in cursive so you know it's an L. I watched some kid type it into Desmos one time. I was like, what are you typing? He's like, I don't know, it never works. I'm like, bro, you're putting I in. It's LN. Anyways, I digress. What if we started off as a logarithm and I wanted you to write it as an exponential?
Would it be
We still ask ourselves the same question. What is the base?
7
to the power of 2 equals x. 7 was the base. The output was 2. Now it's the input. The input was x. Now it's the output. What about this letter B? What is the base? 3. What was the output?
Was?
I heard both answers now.
Why was the output?
Are you sure? Isn't y inside that logarithm?
X.
Whatever is inside the logarithm or next to the logarithm is the input. So what was the output here? X. And so then it should be equal to the old input, y. What about C? What's the base? 10. Nice, you didn't fall for my trick. What was the output? 2, and now it should be equal to y, the old input. Nice. Let's see if you fall for my trick this time. What's the base? E. A natural logarithm has base E. We won't show it to you. You have to know that. What was the old output?
4.
And what's the new output?
C.
Nice. Okay, we get it. Yes? Let's prove we get it. I have a Kahoot for us to play. Is we need to get a little bit better about thinking in terms of logarithms. Because there is a large portion of this class, this test, that you do without a calculator. So I'm going to ask for you to learn to evaluate logarithms without the use of a calculator. But seeing as though we just introduced logarithms really to you today, that's very hard for me to do because this is like me asking you to know your times tables. You've been working on your times table since like 3rd grade, right? Okay, but we need to know our logarithms and how to evaluate them as well. Which means we're going to make this easier on ourselves. And when we are evaluating without a calculator, we're going to utilize its equivalent exponential form and think about power families to be able to get there. Here's why I've been making you do those power family gym kits at the beginning of class for so long. What we're going to do is to evaluate log base 2 of 8. You are going to set it equal to x. This is like a question mark. This is like a placeholder. We're going to do the log loop. What is the base here?
2.
What would be the new power?
X.
And it should be equal to?
8.
So question, 2 to what power is equal to 8?
3.
2 to the 3rd power is equal to 8, right? 2 to the 3rd equal to 8, which means log base 2 of 8 is equal to 3. We have to be able to think about the power family backwards now.
I like that.
2 to the 3rd power is 8, so log base 2 of 8 is 3. Let's try it again. Log base 5 of 25. If we set this equal to something, like an x, this would be 5 to some power equal to 25 once I do the log loop. 5 to the 2nd power is 25. That means that log base 5 of 25 is 2. That's what it's equal to. Once you don't have to do this, like switching it with the log loop, and you can just evaluate them in your head, you're good to go. But if you're stuck needing help, this is how we do it. We set it equal to x, and we do 2 to some power equal to 32. So when we start our power family of 2s, 2 times 2 is,
4.
times 2 is,
8.
times 2 is,
16.
times 2 is.
36.
So 2 to the 5th power is equal to 32, which means log base 2 of 32 is 5. We see how I'm doing this?
Yeah.
Okay. Last one of the easy level.
10.
So yeah, if we set it equal to x, what's the base?
10.
10. So 10 to what power is 100?
Oh,
What?
I'm tripping, my bad.
10 times 10 is 100, but 10 to the 10 is too big.
2.
10 squared is 100, yeah. That means that log of 100 is equal to 2. A trick with log base 10s of like 100 or 1,000 is count the zeros. How many zeros in the number 100?
2.
So it's equal to 2. If this said 1,000, what would it be equal to?
3.
3, because it would be 3 zeros in 1,000. Okay, cool. Let's try some harder ones. How about that? We have log base 16 of 4. This is the ones where it's going to be actually very helpful for us to do the log loop. If we leave our placeholder x, this is now 16 to some power equal to 4. Whoa. How do I make that base get smaller?
-4 for negative.
That's a great idea. Hang on to that for later. How are 16 and 4
Oh.
related?
You can divide by a fractionary.
An exponent that's a fraction, yes. Because if you think about it, isn't the square root of 16 equal to 4?
Yeah.
And how do we write the square root as a power?
Oh,
That's the power 1/2. So if 16 to the 1/2 power is 4, that means log base 16 of 4 is 1/2. 16 to what power is 4? A half.
that is so annoying.
That is so annoying. Is that what you said? Okay, what about this one?
3x.
So yeah, 3 to some power is going to be equal to 1.
1/3.
No. This is an exponent rule we sometimes forget about. Anything to a particular power is equal to 1.
0.
Anything to the 0 power is 1, correct? So we would say 3 to the 0 power is 1. That means log base 3 of 1 is 0. What about this one?
1.
So it would be 10 to some power equal to 10.
1.
1. Very good. 10 to the first power is equal to 10. What about the last one? We have 6 raised to some power equal to 1 over 36.
1 over 100.
Great idea, but no. How are there 6, just regular 36?
6, 1, 6, 2.
If I just wanted 6 to some power to be equal to regular 36, what would it be?
6.
6 to the second power, yeah, 6 times 6, which is 6 squared, is 36. Now, how do I get that 36 into the denominator? We make it negative, which means 6 to the negative 2 would be 1 over 36. So we know log base 6 of 1 over 36 is negative 2. You liked it earlier.
Hardly
Until it got unfun.
before that,
Until it got unfun.
basically.
So let's just take a second again. This is very important for us to be able to do without a calculator because, again, part of your test in this course and a lot of this class is days I don't let you pick up a calculator. So we're going to have to be able to do these by hand. So we're going to play another Kahoot.
No.
We're doing it.
How about not?
Yeah, right now. Let's go. Now, of course, I've made you just do all of those things without a calculator. There is a way you can do them with your calculator. We kind of discussed it earlier. I want to teach you a few more buttons that you can press. Like always, we're going to round these decimals to 4 decimal points. So if I asked you to evaluate log of 9, that is base 10. So 10 to what power is 9? I don't know. That's not in the power 10 family. This is when we would need to use our calculator. So you press the log button. You press the 9 button. You close that parentheses. You press enter.
0.9542.
Yeah, log of 9 should give you approximately 0.9542. 4 decimals every time for me, please. If I go to B, that's still base 10. 10 to some power equal to 6125. Those are not in the same power family, so we use our calculator. Press log. So this should be approximately equal to 3.7871. Those are pretty simple, right? Because we have straight up a button for log.
Do we have to do the weird square root
No, that just means that we've rounded the number. It's more appropriate, but no, you don't have to do it. I would prefer it though. How about C? What's different about C from A and B? It has a little base, right? There's no button on your calculator for the little base, is there? So here's what we're going to need to do. I need you to press the math button. And I'm going to need you to scroll down until you see something called log base. What letter is it? If you press that option A that says log base, it's going to set up for you a logarithm with a space in the calculator for the base and a space for the argument, the evaluated number.
So basically, if it says 3.3219, so I would just put it, keep it at 3.3219, or I go 3.32.
The first option, 3 point. So this one, yes, when you evaluate it, should be approximately equal to 3.3219. Did everybody find that log base?
Yeah.
Can we do it again? Because letter D also has a base that's not 10 and is not E, so we need to go to the log base. It's math and then log base. That's not written or typed anywhere on your notes, so make sure you've written that down. Math and then log base. Maybe give it like a little cloud situation so that we can see it and find it fast. What is log base 7 of 1 to 35?
2.5208.
Yeah, I got it.
Nice. Agreed. Okay, cool. So we get it. We can use a calculator here. I just made you really work hard and doing them in your head. We're going to need to practice more doing them in our head because clearly we can push some buttons on a calculator. I want you to be able to evaluate these functions. Now, a question you may be having is, Why do we even need to do logarithms? We have exponential functions. What is an important use for logarithms? And we're going to discuss this actual topic later. It's the last topic in Unit 2, but we're introducing it early because it's super new. You've never seen this before. One useful purpose for logarithms with dealing with exponential data. Exponential data can be very challenging to display graphically because values start off really small and then get really big really fast. Have y'all ever graphed, I'm sure you have, on Desmos, like an exponential function? If we look at the example here that's printed, this right here is the population of English Americans in the current United States since 1620, clearly not talking about the Native American population that's here. This is like the Mayflower, right? The Pilgrims came. Happy Thanksgiving, everybody. But population has grown exponentially. We have a lot more people in America than we did back then. The estimated population is shown from 1620, right here, to 1820, where t equals 0 is the year 1620. This graph shows us this function in an exponential graph. And if you're only looking at this, what does it look like it's trying to tell me the number of people that were here in 1620? None. Do we think that's true?
No.
We literally know that the Mayflower flew over here. Flew. Boated? Sailed? Sure. Sailed over here at that time, right? So we know that's not true. We just can't see the information because it's so small compared to the population in 1820. So what mathematicians have done is we've created a different type of graph that has been logarithmically scaled on the y-axis. Everybody highlight that y-axis. Do you see how it's not counting by the millions? The one on the right, on the left goes 1 million, 2 million, 3 million, 4 million, 5 million, on and on. This one, which has been what's called logarithmically scaled, is scaled by powers of 10. What's 10 to the first power? 10. What's 10 to the second power? What's 10 to the third power? So what is this graph trying to tell me is the amount of people that came over on the Mayflower. Somewhere between 100 and 1,000. And that makes sense. That's probably a boatload of people, if you will, right? That got here. So in this graph, we're actually able to see these first few points a lot easier than we can here, because that's just too small. Can't read that. So what mathematicians have done is they've taken these graphs, and they're called semi-log plots, and we'll write that down later, and it allows us to see the beginning and the end information of an exponential function a lot easier. Engineers use this. My dad worked in petroleum engineering for years. He's already retired. When I told him I was going to teach this lesson, he got so excited. He's like, I literally use this every day. So this is actually something that engineers use to display their data, because otherwise it's too small or too large to see all at once. So let's just make sure we understand how this works. This is like a copy paste of the graph from the other side. It's a population of data. We're going to add coordinate points to it so that we can understand how the graphing kind of works in these log plots. Okay? The population data, it's the same thing. The year should be graphed since 1620. So how many years since 1620 is 1840? If the year 0 is the year 1620, how many years has it been if it is now 1840?
220 years.
220 years. How about when it's 1860?
I don't even know what you guys are.
How about 1880? How many years have passed? 260. Okay, and we're doing this because that's where we're going to graph on the x-axis. At the year 220, at the year 240, at the year 260, after 1620. Now the population that we have here says that we should have 17 million, 31 million, and 50 million. If we write this in scientific notation, this is 1.7 times 10 to what power? If I put the decimal point right here between 1 and 7, we had to move it 1, 2, 3, 4, 5, 6, 7 times. So what we're saying is that this coordinate point, 17 million whatever, should be at 1.7 above the 10 to the 7th line. Here's the 10 to the 7th line. We should be just a little bit over the 10 to the 7th line when we graph that coordinate point. we should be 1.7 over the 10 to the 7th line. What would the middle number, the 31 million number, be in scientific notation?
3.1
Times 10 to the 7th. So again, at 240, I can be at approximately 3 above the 10 to the 7th line. What would this last number be in scientific notation? 5.0 times 10 to the 7th power, which means we should be halfway between the 10 to the 7th line and the 10 to the 8th line. So we were able to add, in one graph, display about, 700 people, all the way to 50 million people in this population graph. This makes the graph so much more useful to scientists and historians who are looking at this data to draw conclusions, because we can see it all at the same time. The last thing we're going to practice today is actually plotting these coordinate points on the type of graph you will see in AP Pre-Cal. This graph right here, which is more detailed than the 10 to the 7th graph was, is exactly what's called a semi-log plot. It's called semi-log instead of log-log plot because only one of the axes is scaled logarithmically. We notice this right here is all scaled logarithmically. We are still doing powers of 10. This is, the bottom one is 10 to the 0 power, 10 to the 1st power, 10 to the 2nd power, 10 to the 3rd power. But what do you notice I've now given you in between those major powers? There's like a bunch of lines, yeah? How many lines are there? There is 10 in each, which gives us a way to plot different points. If I wanted to plot the coordinate point 1, 20, I would still go to the 1 on the x-axis. That's easy.
You go up 21.
I would go up 20. How do I do that? What do you mean by go up 20?
Count the lines. Oh, wait.
We'll count the lines, but like this entire chunk right here is representing 1 through 10. This entire chunk is not representing 10 through 20.
11 lines. Wait.
So if this is 10,
And then anything up.
One and place it on the second line.
very good. This right here would be 1, 20.
And then that would be, if you go from 100 to 1,000, it's each line worth 100.
Correct.
Okay.
Did y'all hear what Corey said?
Yeah.
Every line above 100 is going up by 100s. Then when we get to 1,000, every line is going up by 1,000. We would
So
get
it's
to the
like-
next one. It'd be going up by that power. Yes.
Would be the third line or the second one? Or the second line?
So that's a great question. The next one we're going to graph is 2, 300. If I want to go to 2, 300, here's 2. This bold line is 100. So what's this one?
200.
So what's this one?
300.
There we go. That's where we're going to put it. You guys are getting it. The next one I want to graph, C, is 3, 2. So I go to the x value of 3. This bold line is 1. So where's 2?
The next one.
Just right above it. Interesting. Good eye.
If it's 15, would it be like in between, in between 10 and 20?
Okay, so the question is, for 15, would it be between? Yes. So I know that this line right here is 10, which makes this line 20. So where's 15? In between. Nice. So this is going to be 15. So where's 5, 350? In the middle of the third line where?
Between.
So I got 5. I'm going to go to 100. This is. So I want to go right in the middle of those. Okay, nice. It is. You're going to be asked to read semilog plots and verify that semilog plots have been representing their correct function. There's an entire lesson on semilog plots because there's more to it than this, obviously. But we want to introduce it to you early so you don't ask us the question like, why are we learning this? This is why. This is used in a lot of industries, a semilog plot. How do we feel about this?
Not becoming an engineer.
Not becoming. Yes.